The star has been burning for 8 million years. 8 million years of silence. 8 million years of light pouring across the darkness, warming nothing, touching nothing, witnessed by no one. A red supergiant 700 times wider than our sun, sitting in the spiral arm of a galaxy doing what stars do, burning, fusing, surviving, and then in less than a quarter of a second it stops. Not slowly, not gradually. In the time it takes a single neuron to fire in your brain, the entire core of this star, a sphere of iron the size of a city, collapses, 30 kilometers across in a fraction of a second. The implosion is so violent, so instantaneous, that the outer layers of the star don't even know it's happened yet. For a brief, strange moment, the star falls inward while its surface still thinks it's alive. And then the shockwave hits. What comes next is the most violent event the universe is capable of producing without destroying the fabric of spacetime itself. And if you were anywhere nearby, if any living thing were anywhere nearby, there would be no warning, no time, no escape, just light, and then nothing. From a distance, it looks like a new star appeared. That's actually what astronomers called them for centuries. Nova, from the Latin for new, a bright point of light where no light had been before, flaring up in the night sky, holding for weeks or months, then slowly fading. Ancient Chinese astronomers recorded one in 1054 AD. They called it a guest star. It was bright enough to see in full daylight for 23 days. For nearly 2 years, it was visible to the naked eye at night. What they were watching was a star dying 6,500 light-years away. What that dying star left behind is the Crab Nebula, a churning, expanding cloud of superheated gas 11 light-years across, still growing, still violent, still radiating across every wavelength of the electromagnetic spectrum. At its center, a pulsar, a neutron star the size of a city, rotating 30 times per second, a remnant so dense that a single teaspoon of its material would weigh 10 million tons on Earth. That is what a star leaves behind when it dies quietly. But here's the problem. Not all supernovae are quiet. The moment the iron core collapses, something happens that defies intuition. The core doesn't just shrink, it rebounds. In the first milliseconds after collapse, the density at the center of this dying star reaches the density of an atomic nucleus. Neutron degeneracy pressure, the quantum mechanical force that keeps neutrons from occupying the same space, slams the brakes. The infalling material hits the newly formed neutron core and bounces back outward at 70,000 kilometers per second. That's nearly a quarter of the speed of light. The resulting shockwave begins tearing through the outer layers of the star, but it stalls almost immediately, losing energy as it battles through millions of kilometers of stellar material. And this is where things change, because what reignites the explosion is something that should not be capable of doing anything at all. Neutrinos. In the first 10 seconds after core collapse, the dying star releases more energy in neutrinos than our sun will emit in its entire 10 billion year lifetime. 100 times more energy than our sun has ever produced. The number is almost meaningless. 10 to the power of 46 joules, released in less time than it takes to draw a single breath. Neutrinos are so weakly interacting that they pass through the entire Earth as if it isn't there. They pass through you right now, billions per second, without touching a single atom. But in the collapsing core of a supernova, the density is so extreme that even neutrinos get trapped. And when just 1% of that neutrino flux is absorbed by the stalled shockwave, just 1% of an incomprehensible number, the explosion restarts. The shockwave tears through the remaining stellar envelope. The star's outer layers are launched outward at up to 30,000 kilometers per second. 3% of the speed of light, in every direction, simultaneously. But it gets worse. What actually gets ejected in this explosion is not just gas and dust. It's the periodic table. Every element heavier than iron that you have ever touched. Every atom of gold in every ring ever worn. Every atom of iodine in your thyroid. Every atom of barium in your bones was forged in the final seconds of a collapsing stellar core. The rapid neutron capture process, the R process, happens in milliseconds during the collapse. Nuclei are bombarded with neutrons faster than they can decay. Unstable isotopes cascade into stable ones. Heavier and heavier elements are assembled in a nuclear forge that exists for less than a second and then is gone forever. When the shockwave throws that material into space, it carries those elements with it. A single supernova can eject several times the mass of our entire sunday. That cloud expands for thousands of years, sweeping through the interstellar medium, seeding molecular clouds with the raw material for new stars, new planets, new chemistry. You are made of this. Every atom of iron in your blood was forged inside a star that died before our sun existed. The calcium in your teeth, the oxygen in your lungs, the carbon that forms every molecule in your DNA. You are, in the most literal sense, a collection of supernova debris that learned to think. And this is where things get existential. Betelgeuse is dying. You can see it on a clear night in the constellation of Orion, the reddish star on the upper left shoulder. It is a red supergiant, 700 times wider than the Sun, sitting approximately 700 light-years from Earth. For the last several years, it has been behaving strangely. In late 2019 and early 2020, it dimmed dramatically, what astronomers called the Great Dimming. It shed a massive cloud of material that cooled and blocked its own light, pulsated, convulsed, and then it brightened again. But here's the thing about a star that is in the final stages of nuclear burning. We cannot know exactly when the core will collapse. The iron core builds slowly by human standards, not stellar ones. Could happen in 10,000 years. Could have already happened. If Betelgeuse went supernova 700 years ago, the light from that explosion is currently traveling toward us at 300,000 kilometers per second, and it will arrive without warning, without any way to detect it in advance. And for several weeks, there will be a second sun in the sky, bright enough to cast shadows at night, visible in daylight. But that's not even the worst part. The worst part is not Betelgeuse. The worst part is the ones we are not watching. There are an estimated 400 billion stars in the Milky Way. Of those, a small fraction are massive enough to die as core collapse supernovae. Astronomers estimate that our galaxy produces somewhere between 2 and 12 supernovae per century. The last one visible to the naked eye was Kepler's supernova in 1604, over 400 years ago. Statistically, we are overdue, and the dangerous distance is closer than most people realize. A Type Ia supernova, triggered not by a collapsing massive star, but by a white dwarf silently stealing mass from a companion until it explodes, would need to be only 3,000 light-years away to noticeably affect Earth's biosphere. Its gamma rays would strip away ozone. Its cosmic rays would bombard the surface for years. The closest known candidate for this type of explosion is a white dwarf in a binary system called IK Pegasi, just 150 light-years away. Astronomers believe it is probably 1.9 billion years from detonation. Probably. The dim white dwarf does not announce itself. It has no bright light to watch, no dramatic pulsation, no great dimming. It simply accretes gram by gram across millions of years. And one day, in a millisecond, the carbon ignites. Runaway nuclear fusion tears the entire star apart in an explosion bright enough to temporarily outshine its entire host galaxy. No core survives. No neutron star. No pulsar. Nothing. The star simply ceases to exist, and its death is visible from billions of light-years away. In 1987, astronomers detected something that had never been detected before. 23 subatomic particles. Neutrinos arriving at detectors buried deep underground in Japan, in the Soviet Union, and in Ohio, arriving 3 hours before the light from supernova 1987A in the Large Magellanic Cloud reached Earth. 3 hours before anyone saw the explosion, the neutrino flood from the collapsing core had already passed through the planet, through every person alive at that moment, through you, if you had existed then, without anyone knowing. The universe sent its warning. We only understood it after the fact. This is the nature of the cosmos that surrounds us. Its violence does not ask permission. Its timelines are not calibrated to biological attention spans. It operates across distances so vast that a star can explode and its light spends longer traveling to us than our entire species has existed. The iron in your blood was made in a star that exploded before Earth was born. The explosion that made it was more energetic than anything our civilization has ever conceived of. And somewhere, right now, in the quiet dark between the stars, another core is failing. Another iron mass is crossing its final threshold. Another shockwave is beginning its journey outward. The universe makes its heaviest elements in catastrophe. It makes life the same way, and neither asks us first,